So last few things, like I just summarized. So I covered, in fact, all these algorithms in this course. Okay. So let's just summarize interpolation. I started with that. Then we did integration, which was based on interpolation. Then we did differentiation, which is again based on interpolation, right? So PN, that Lagrange interpolation polynomial. Then once we had integration, then we did ODE solvers based on integration. And once we had ODE solver, I could do PDE solvers, right? And PDE solvers are three of them, in fact. Finite difference, spectral, and Laplace. Okay, there were the three differential equations. Okay, and they are, at least these two of them are based on ODE solvers. For the structural method, we also needed some fundamentals of Fourier transform. So it is covered here. Boundary value problem. This was initial value problem. Now we can also do boundary value problem given ODE solvers, right? It had guess the slope and get there. And for that, we needed to use some nonlinear equation solver, okay, root finders. So root finders were here. So these are all connected, okay. And linear algebra is kind of standing alone, but it had application in finite difference, differentiation, as well as interpolation. Spline linear algebra was used, and Monte Carlo is kind of separate. Okay, that's a connection. So I try to make this connection explicit in this course, and I hope you liked it. Secondly, some tips which I did say it in the beginning, but let me just repeat now, since the course is getting over. So I think it's very important to focus on these tips. But all of you will need programming. Okay, either you work in research or industry, you will need to program. I mean, even managers are now learning Python. Okay, so I think so. Few things you should keep in mind: that you should solve the problem. Don't get to writing in a laptop right away. Okay. Think of algorithm first, then write the pseudocode, then write your program. Okay. If you are a manager, then you don't need to get here, but you need to think of algorithm. If you want to be a good manager, some of you who want to go to industry, you should know how to solve the problem. Okay. So a lot of it is a clever algorithms. Okay. I mean, Amazon is Amazon because of their clever algorithms, and the top managers know how to solve those problems. Think of extreme cases. Okay, this is critical for all codes. Codes will break if you don't think of extreme cases. Okay, code slowly. Don't rush, because fast coding will be leading to a lot of bugs. Code in parts. So this is where object-oriented programming becomes very useful. But Python offers you that. I mean, you can think of a part and put it in a file. Think of another part, put it in a file. Then you can use import and you can call one from the other. Okay, so Python is really nice. I mean, it's simple, but it's great. I mean, it can do things. Code with confidence. Okay, you should have the confidence. Otherwise, you can't really write good codes. First, write the code that works. Okay, then make it efficient. Okay, we didn't think of efficiency except vectorization. Okay, but you should not write a dirty code. But don't think of like writing a very clever code in the beginning itself. Write a working code which is clean, easy to read, then try to make it efficient. Okay. There are efficiency tricks, okay, which I didn't do it except vectorization. Okay, but whether I'll offer a course on parallel computing next semester. You are welcome to register if you're not registered already. So it's called HPC and applications. It's IDC Interdisciplinary 606A. And comment your code. It's a good idea, but I hardly commented. These are small codes, but I will comment my, at least this like a sandpile model requires comments. Okay. I may forget what I did after some time, so I need to comment. That's where the writer himself or herself forgets what is done. So it's a good idea to comment what is done there. What next? So these are codes which are saying max 50-line codes, But if you have code which is like 10,000 line codes or 1 lakh line codes, then you need to do structured programming. Okay, you really need to think of full design. Okay, and that's where the object-oriented programming, which is possible in Python itself. Python has objects, okay, classes and objects. But if you large code, then C++, Java is used. Parallel programming for, like I was just telling, 50 by 50 Ising spin, I can do it in a laptop. But if I just make it 500 by 500, then I need to parallelize it. Okay. That means I need to use many machines. Part of it will be done in one machine, part in another machine, and then combine the result. Okay, so that's parallel programming. And use libraries. Okay, so Python uses a huge number of libraries. Like I was using ODInt, for integration. I was not using my own Euler. Okay, ODInt. I mean, you should use. So you may say, well, why did we learn all this interpolation, integration? They have their value. I mean, when I write this big code for fluid mechanics, I cannot use ODInt. Not possible. Okay. It has like million equations. Okay. And sometimes it has to be done with the equal time step. And so ODInt is no good for large problems. So that time we need to know which one is a good algorithm. So we wanted to solve Euler equation, which is energy conserving. So we needed to know, I mean, I can't use Runge-Kutta fourth order. That doesn't work for energy conservation. So we had to use advanced version of leapfrog. Okay. So if you are into computation, then you need to learn all these tricks and something more. Okay. So there are numerical algorithms which was done by Gauss and Newton and so on. I mean, look, when I started teaching the course, I did not really relate that Newton was doing Newton root finder. Okay. But it's interesting, no? I mean, this great physicist, he's not thinking that solving this equation is some low-level work. They are interested in finding a root of equation. Okay, so in fact, that's what I think. I do want to emphasize that. Okay, I cleared JEE, I'm a great guy, and I don't want to do simple things. You should do simple things. Okay, everybody, and that's where you find interesting ideas in simple things. And I think so. That's what's inspiring for me. Like Gauss is doing this quadrature. I mean, somebody says, well, nowadays, integration is very easy. But no, he's really coming up with a clever algorithms that is lasting for 300 years. You see, that's the greatness of that algorithm. Okay, limits of computation. Okay, now, right now is a fact. Anything can be done by computers. Okay, now, why is it? Okay, limits of computation. Now, is it true? I mean, how many of you think is true? Does computer have limitations? Okay, let's take a vote. I mean, this one-way traffic, I'm also bored. Okay, please put all problems can be solved by computers. Okay, I already put some in. So people who think all can be solved by computers, at least approximately put 1. Solve 1, so not solve 0. Okay, good. So they agree with me. But by the way, many experts think that all things can be solved, at least in practice. Okay, I mean, now there is a fact that, computers can draw great paintings. Okay, computer can write poetry. A computer can do all sorts of things. Okay, I don't think so. Okay, I mean, that's my personal belief. But it also, people have done this. We are kind of ignoring those great works. Some problems are unsolvable. And do you know one example which I gave in the class? Which problem is unsolvable? It is proven. It is not solvable. Anyone from computer science? Which problem is unsolvable? You can unmute and speak. P, NP, okay. And NP problems can be solved. It just takes longer time. I don't know what is three-set problem. Give me a simple problem which can't be solved, which you did in the course. Look, this is where halting problem. Great, Abhishek. Okay, halting problem we did in the class. I think I did mention it. So the idea is that you write a code which will figure out, well, basically this is a code, general code G. Input to this code is any program P. Okay, so program P I put as input and figure out whether the program P has infinite loop or not. Okay, it should be any general program. Okay, so we take a P and put it inside a G, and G should say that okay, it has infinite loop or doesn't have infinite loop. This is a simple statement. Okay, and this is called halting problem. I mean, if you can write program G, then great. This is the solution to halting problem. And it turns out Alan Turing, he showed that this code is not possible. Nobody can write this program G for a general program P. So halting problem which is finding a halting problem is that you write a program G which can take any program P as the input and gives the result yes or no. Yes means it has an infinite loop, and no means it has no infinite loop. It turns out nobody can write this program G. Okay, so this one problem is unsolvable. Okay, so however clever programmer is or computer is, no, it cannot do it. Also, this is an interesting argument. F of x. So x is lying between 0 and 1. Okay, in that range. How many f of x are there? Okay, f of x also lies between 0 and 1. Okay, so this is a function in this box. I can draw many functions. No, how many functions are there? Anyone? Again, in computer science you do it more often, but in physics also you may know. There are infinite of them, right? But infinite is also there are number of integers from number of integers also infinite. No, so I mean there's no largest integer. It is infinity. But is it as large as the infinite integers? This infinity, in the number of integers is infinity. But f of x, is it as large or even larger? Anyone? What do you think? Okay, make a guess. Chat. Is it as large as 1? But larger is... So which is less large? I mean, integers is less large. So if it is f of x is greater than you write 1, or f of x is as large as integer, write 0. So number of functions is less. I see. 0.5 is not possible. Okay. Okay, I'll give the answer. The f of x is bigger infinity than integers. Okay. So integers is called countable infinity. Countable infinity, and this is called uncountable infinity. Okay. You cannot count the number of fx. Okay. And this again algorithm comes from not Turing, but I think is by Cantor. Yeah, this is by Cantor, who defined various chords of infinity. Okay, so he gave this stuff. So number of functions is more than number of integers. What does it say? So number of programs must be equal to number of integers, right? I mean, your programs have alphabets, no? So number of programs cannot be bigger than number of integers, right? You agree with me? Okay, all possible programs, I mean, whoever can write, it will be countable infinity. But f of x is uncountable infinity. That means there are some functions which cannot be obtained by any program. Okay, those functions can be approximated by some program, but they cannot be obtained exactly by any program. Okay, so this is another way to say that there are functions which cannot be programmed, or cannot be, we cannot write a program to generate that particular FFX. Of course, we know that we cannot get infinite digits, right? I mean, any program, RAM is limited, so there are limitations. But these are nice proof, is mathematical proof that there are some functions which cannot be, we cannot find even by like large number of loops, just or infinite memory also we can't do it. Okay, so programming human intuition and emotions. Some people think that it can be done, but all this AI is all into it. But I mean, self-driving car or chess champion. Right now, the chess champion is a computer. It's chess champion because it can compute fast, and it also has a lot of database, and it can search fast. But not clear that it can get this intuition and emotions. Okay. Anyway, so this is what I wanted to say. But there are things can be done. I mean, I'm happy that I know some computing, and there are problems which can be solved, which remain unsolved, and it can also be good to people. I mean, good for like weather forecast is nice. We can automate things. All the drudgery can be automated, so that we can do enjoyable things and creative things, which we like and we enjoy. Okay, happy computing, and I think I will stop.